as a microprocessor. Some technically, but most people just still call it a CPU, or some people still call it just simply a processor. So that's one of the things that, if you looked at your cell phone or we call them cell phones, but they're actually smart devices, right? One of the things is what processor does that thing run? And usually, they either run a faster one when they come out with different versions, or they go to a different model of that. So my computer's running what they call an i5 processor, which is put out by Intel. I don't know what version it's running, but this guy here, the microprocessor in this computer still has the same basic units. It's got a microprocessor, right, or a processor. It's got input. It's got output. What's the next thing? Well, input, output is interface. Memory. It's got memory. So that's the four things that any computer is going to have. So I bring up my cell phone. What's in my cell phone? A processor, input, output, and what? And memory. Now we got all types of categories of memory. We got some ports that's called I/O ports. These are ports that are bidirectional, so not only would they be able to send data out, but they'd also be able to bring data in. So we looked at the ROM. What's ROM? Read-only memory, and we looked at the different categories. We have ROM, which is basically the information, and that's read-only memory, which means we can't do what? We can't write it. We can't change it, which made sense. It's like my automated nervous system would be what we call our ROM. So you're born with that. As soon as you're born, you can breathe, you can see, you can hear, and then that's your ROM. We don't want doctors to go in and be able to change our automated nervous system, or we would probably kill us, right? We'd go blind or something like that. So this computer's probably got ROM in it, but usually the problem with ROM is it's really hard. The only way that we can upgrade, if something changes, the only way that we could upgrade would be able to pull that chip out and put a new one in. And then that means the chip itself is going to have to be in the socket, and automatically you start adding more cost to the cost of the system, right? You understand? So they came out with something called PROM. What's PROM? Programmable read-only memory. This basically is a one-shot deal. We could program it in a programmer, but once we program it the first time, if we wanted to do it, we couldn't pull the chip out. We definitely can't program it inside the unit it's intended to operate in. So we have a special unit called a PROM programmer, and we've got one around here somewhere, guys. But it's a one-shot deal. So what they did is they came out with something they call an EEPROM. And what's an EEPROM? Erasable programmable read-only. And this is the one I passed around the other day. I didn't bring it back over, which actually has a little glass window in it, or quartz window in it. And if we expose that window to high intensity short wavelength ultraviolet light, it will erase it. It sets all of them to 1. And then we could program it in the program. So what was nice about the EEPROM, and these are still very popular, especially if you don't want somebody like me or some basic person going up there screwing up the ROMs in the computer. Because the ROM, so what can a processor do? A processor can do one thing. What's the one? Run programs. So that means when we turn power on the computer, what happens? We call it a reset. When you power this thing up, it goes to an address in memory looking for an instruction. That's all it can do on its own. And then after that, it is under total control of that program, right? So it means we've got to have a section of memory in our computer that is non-volatile, which means what? It does not lose its content when power is removed. That's what non-volatile means. Plus, you don't want people going in around screwing around with that thing, right? You understand? So that's why we have this ROM in there. So EEPROM makes it still a little harder because you would still have to pull it out, put it in an EEPROM eraser, which is nothing but just a nice big fluorescent bulb without the shielding that's up there. So fluorescent bulbs put out ultraviolet light, but they shield it, so it's not going to really affect us that much. You can erase a EEPROM just by exposing it to sunlight. It's just that you would have to probably put it out there about 4 or 5 days for there to be enough ultraviolet light to erase it. And this is why usually on an EEPROM they'll put an opaque label on it, right? So you won't accidentally erase it. But what they do is they'll put the version number and all that other kind of stuff on it. Then they came out with a double EEPROM, and this is where we're at right now. What does double EEPROM mean? Electrically erasable, programmable read-only memory. So if your computer has the right circuitry in it, we can still make double EEPROMs where you can't erase them. But if you have the right circuitry in your computer, then you can erase them. But usually it takes a special application. So every once in a while it says you need to update the firmware in your machine. And you better really make sure you got a really good power source, because if you're updating your firmware, or you're updating your basic operating system, then you could be screwed, right? You understand? So now most of your devices run what we call double EEPROMs. Some people call them flash memory. They'll say we used to, when we made these EEPROMs, or these programmable devices, we called it burning. We said we need to burn a new ROM. And this came from the technique of PROMs, where we actually literally went in there and blew fuses inside the chip to generate that. So we called it burning. Well, when they came out with these double EEPROMs, the term is usually changed to flashing. So if you hear the term flash memory, that's where flash memory comes from. And these are devices that we can electrically erase and reprogram. So what that means is now, if you've got a small error that pops up in your ROMs, then you'll get a flash up saying you need to flash those things, and you'll run a special program, and it tells you right off the bat, you better not do what? You better not turn it off, and also you better have a good access to an internet. So usually you want to make sure you use a hardwired access to the internet, and try not to use Wi-Fi. So double EEPROMs have different names. USB, these are double EEPROMs, but these are mass storage devices. So when we talk about the ROMs, we have two terms, what we call firmware and software. Anybody know the difference between firmware and software? Well, it depends on what type of CD it is. But what is firmware? It's really good. People understand CD. But what is firmware? Well, firmware is programs that are really hard to change. You had to change. Usually to change your firmware, you had to change hardware. And what is hardware? If you can touch it, it's hard. If you can touch it, it's considered hardware. Now, usually when we talk about hardware, we're talking about devices that are controlled by programs, but you can touch it. So a disk drive would be considered hardware. A USB, the stick itself would be considered hardware. The information you store on it would be considered software. Y'all understand that? So firmware is information that is extremely hard to change. Now, even flashing, you have to have special applications to flash the firmware in the machine. And you don't do it often. Right? You understand that? Software. What's software? That's programs that are easy to change. Well, you can't say it's the actual programs that we run, because when you boot your computer, it boots into firmware. And those are programs, right? You understand? So if all the microprocessor can do is run programs, that means it's got to have programs that it runs when it comes to life. And those are firmware. Those are programs that are never intended to be changed. But since we have flash ROMs now, we have the ability to change it, but it's very, very what? Seldom. Software is intended to be changed. That's why it's called soft. Right? You understand that? So USB drives, what can you do with those? You can erase them, you can reprogram them, your mass storage, just about every mass storage device you have is considered software. That makes sense. We have what we call an operating system. These are programs that run the computer. And basically, these consist of a little software called drivers. Y'all heard of drivers? What's a driver? You see it pop up all the time. You stick a new USB drive, little stick on there, a little thing will pop up saying I've got to load the driver or something like that. Well, a driver is a specific piece of a program that is attached to your operating system. So an operating system is nothing but hundreds of drivers. A driver is a piece of software that makes hardware work. So I've got a driver for this display. Y'all understand that? I've got a driver for my USB thumb drive when I plug it in. If it don't find it, what will it do? It'll install it for you. This came out with something called PNP, plug and play. So most of your USB drives has a standard set of little firmware built into it. When you access it, it automatically says, I'm out here, and this is my driver. And then your driver will automatically be added to your operating system. And then we have something called a shell, which is allows you to control the operating system. So when I come out here and look at this is my shell. So what do I do with my shell? I can run programs. I can delete things. I can do this, but I'm doing it through drivers, right? You understand that? So what I'm doing when I use my shell, this is a program that allows me to control the operating system. What did you say a driver was? A driver is a little program that's designed to run a specific piece of hardware. So you got a display driver, you got a keyboard driver, you got this, and so and what's nice is you go out and buy. A lot of times you go out and buy a new adapter card, especially on a desktop, and it'll come with a little CD, which has the wire, has the driver, and then we have applications. What's an application? Y'all hear that all the time. Go to the app store. Well, that's an application. An application usually don't have any drivers in it. Where's all the drivers at? Well, all the drivers in the operating system, right? You understand that? So an application applies the operating system, right? You understand, to run a specific task. So applications usually don't have any drivers in them, but if you compile it or create it for a certain operating system, then they apply it. They call it an API. It's an application program interface, which basically you put into your application if you write programs for this computer, and then that becomes part of your application, and that's all your application does is just apply your operating system to do different things, right? Which is pretty interesting. So my PLC's got an operating system in it, and then of course we have the ability to create application programs. So we're going to use a program that's got the API in it. We call it RS Logix. And it's nothing but an application program. It has no drivers. But what does it do? It applies the operating system to run this PLC. It allows us to create applications. So y'all going to be programmers. That's what we did. Y'all going to write programs. Or not write them. You're going to create them. You could draw them. So the language that we use is a graphical language called ladder logic, which we'll look at. So, but this is kind of a little different in PLCs because they call the unit that controls the computer, which is actually the computer itself, they refer to it as the CPU. So it's kind of not right. So basically, and we have two categories of PLCs. We have what we call modular, and then we have what we call fixed. Most of your computers now are a hybrid, which means they start out as fixed, but they do give you the ability to add modules. So this is the little Siemens PLC. And it starts off, it's got a number on it. This is the CMAC. CMAC. It's what Siemens calls their PLC. S7-1200. And it's got the CPU that says it's a lot. That's purple PC. This means we power it with DC. The inputs are DC and the outputs are DC. We'll specify three things about a computer. This is a fixed PLC right now. So a fixed PLC means, got to remember which way I'm going. It's going to have so many inputs on it, and this is where I connect to the inputs right here. This is where I make physical connections to the input. And then it's got so many outputs. No, these are ends. I'm sorry, D ends. And these are D outs. I got that backwards. But they call this, they call it a CPU. So it's kind of a misnomer or misname. But what we have is we have this little door on the side, which we can pop out, and then there's a plug in there that I can plug in other modules. So this basically can be a modular PLC, or it can be used as a fixed PLC, which I technically call a hybrid. So most true modular PLCs, you have a CPU, and there's no inputs, outputs on it. And then what you'll do is you'll add modules to it to determine what you want. What's nice about adding modules, if you buy a fixed PLC, then what you buy is what you get. If you buy a modular PLC, then you can make it what you want, right? You understand? Does that make a difference? That's the difference between buying a desktop computer, a true desktop computer, which has a separate CPU and then a display, or buying these guys right here. So these guys right here are basically non-upgradable, right? You understand? They're very limited upgradable. So when I go out and buy a tablet, that's not upgradable. What is that? You get what you buy, right? You understand? If I go out and buy a true desktop computer, then I decide what video I want. I decide what I this. I decide that, right? You understand? Which is a lot better. So my main computer at home that I like to use with a big display is a desktop, because I can change it, right? You understand that? So fixed and modular, and both of them have advantages over the other. But most of your small PLCs like this are actually hybrid units. So you can do what? You can use them as fixed, or you can upgrade them. You can add different modules for what you want. In fact, they've actually got a little slot right here. I've gotten it in there. This right here pops out. And this is another module that we can add. So what we did here is add more analog on it. The PLC comes with two analog input ports, but what we've added here is analog output, so, which is pretty neat. So this is unique on this Siemens PLC. And then the microprocessor's got RAM and ROM, but the ROM can be different variations. But from our point of view, ROM is ROM, whether it's EEPROM, whether it's double EEPROM, it's something that we right now don't have the ability to change. It's read-only, non-volatile. The RAM, which is random access, this is a volatile memory, which means what?
It can be lost.
It will. If we turn power off, it's gone. So the big thing is how much memory you have. Now, a lot of the memory in the cell phones is RAM, but we have a battery out there that does what? Keeps it on there. And that's why it'll shut off when it gets down to low. If you ever take that battery out, then odds are you'll lose all your applications. Now, the phone will still boot. Boot is a method that we tell it to load its main operating system. Well, you ever heard that term before? Boot a computer. That's whatever you do to make it load, go back to its its basic operating system, which we call a BIOS, which is a basic input-output system. And that's what births the computer when it comes to life. So your BIOS is going to be over here, right? And then, so a lot of times people will get confused with mass storage devices and memory. And unfortunately, it's just like batteries. People don't understand a battery means more than one. So we go out and buy a little we go out and buy a AAA, we call it a battery, but technically it is not a battery, it is a cell. It only becomes batteries if I put two of them together, right? You understand? But people don't understand cells. They don't understand batteries. So commercially, everything that generates DC chemically, we call it a what? A battery. So this is the problem we have, is that these go out to standard people or regular people that don't have all this terminology floating around in their head, and they don't want to call it, well, that's not memory, that's mass storage. So a lot of people just call any device that you can store information on, they call it what? Memory. And so we have trade and then we have actual, right? You understand? It's just like we call a board a 2x4, but if you measure it, it's not going to be a what? 2x4. Because it was set up so it would give you 2 inches when you put a 1/2 inch sheetrock on the outside. Right? You understand that? Then it would measure what? Then it would measure 4 inches. So it means you'd know how far out you would have to come. But everybody calls them 2x4s, but they're not, but that's what we call trade terminology and then actual terminology. So just about anything, so we call USB, we call those memories. We call hard drives memory. We call all these things memory, but those are not memory because memory is inside the computer. Y'all understand that? These are what we call mass storage devices. So this is a mass storage device. Is this part of my memory? But where's my memory at? Here, right? You understand? So what do? Well, I take this and I read it through an input port, right? Into my what? Into my real memory. And then when it gets in there, I can process it. Well, these are your CDs. These are your hard drives. These are your solid state memory. These are your little USB sticks. These are actually mass storage devices. They are not memory. But if I call them memory, is that okay? Sure. Right? I'm not going to correct somebody because that's the commercial name of just about anything that stores stuff for a computer. They call it memory. But you need to understand the difference when we talk about this memory and then mass storage devices. So computers use mass storage devices just like we use books. It holds information until we're ready to use it, right? You understand? But if I'm going to use it, I'm going to do what? I'm going to bring it in through an input port, right? Which is my what? My eyes. It's going to go into my brain. Then I'm going to process it. So my memory is up here, right? You understand that? And my operating system's up here. So we have what we call that automated nervous system, which is basic operating system, but we can add to our operating system. Now, one advantage of loading your operating system off a mass storage device is that we can change operating systems. We can upgrade operating systems. And how often does your cell phone update its operating system? Quite often. Yeah. Too often, right? But you got to understand an operating system is massive. So what they do, it's even on applications, is you got all these engineers but writing this stuff, but you got to understand these guys are technically savvy and they do things right. Then they'll put it out. They call them beta testing, and they'll allow you to have the application, and then when they get it, then these people are still pretty savvy, and then they release that thing out to John Doe, and we do things that these guys can never anticipate that we're going to do. So what they used to is the operating system came on a floppy disk, and we had no access to an internet. So what would happen is when all this stuff started crashing and stuff like that, because people was doing all this crazy stuff, they'd come out with a different version. And then you had to go out and buy the new version. So we was having DOS 3, DOS 3.1, DOS 3.2, DOS 3.3, and every time they came out with a correction, it was still the basic operating system, but either they added something to it or they fixed something that they didn't anticipate. So now what can we do, which is really neat? If you got Windows 10, they don't put out, they keep putting out different releases, but how do they update your operating system? Yeah, and you don't have to buy them, which is pretty good. So your cell phone, I don't know what version, mine just updated again this weekend. Address bus, data bus, and this is not extremely important to know. This is one of the pictures I have in one of the book I wrote. So this is very fundamental, very. So what I have is I have all these devices out here that I'm drawing these mailboxes. And then we have 3 buses. We have what we call the data bus. The data bus is where actually information is transferred. So the more wires you have on your data bus, the more information you can send within one time. Right now, data bus sizes are 128 wires, but basically we're only dealing with 64 at a time. That's a pretty good deal of information. Then we have what we call an address bus. So the address bus is just a group of wires, and notice it's called a bus because we run the wire out through the system, or the conductor out through the system, and then everything just does what? Just taps on it. We call these buses. So you have a power bus, you hear all these different names. So this is called a data bus. So these are just a group of electrical conductors that run out all through the system, and then everything just does what? Just taps. These are connected all the time, by the way. It's just that only one of them is going to have the door. So what we do is we put a binary address out there. Well, binary address goes up the wall. The address bus. We have a special circuit out here called an address decoder. And all that guy is just sitting there looking at the address bus. And of course, the address decoder on the mail system is the mail system, right? Understand? The address decoder for cell phones is basically your cell phone. If you got a hardwired phone, it's AT&T. They've got all this switch gear out there that routes it out to a wire, but your address decoder is built into your phone. So, which is pretty neat because that's in a flash ROM. So what can they do? I can take this in and have the number change. So what happens is your cell phone is receiving everybody's information, but it's doing it through the air, right? You understand? But you got an address decoder in here that's looking for what information? Your number. Now inside the computer, these are actually literally wires because we got to do this extremely fast, right? You understand? And then so connected to the back of this mailbox is a special circuit called an address decoder. And what's the address decoder doing? Well, it's looking for that mailbox address to come out the address bus. As soon as that mailbox's address comes out the address bus, what does it do? Well, it opens the door to the mailbox. And then that connects it to the data bus. Everybody okay? This makes sense. Now we need to tell it what the heck what are we going to do? Well, mailboxes, we have 2 different things we can do. We can either put mail into it or we can do what? Take mail out. Well, the memory has got to know, or the I/O device has got to know what that program's asking for. So we have another bus that's very fundamental called the control bus. And in this situation right here, it says I'm either reading or writing. So right here it says I'm reading. So what would that tell? Well, if it's reading, it says, okay, I'm reading. The processor's trying to read. Then what it will do is it'll put data on the data bus, and then all the microprocessor does is just read the data. So how many things can we have on the data bus at any one time? One. But we do this at a speed that we just can't understand. I mean, memory buses are running up in the gigahertz now. Which is a billion, I'm not saying 1,000 million. So we do this extremely fast. And this is basically the way this works. So what we have to do is these addresses are binary addresses, by the way. So with the 3 address bits, I can only select 8 addresses. I'm not sure the address bus size now. They're pretty big. I think it's around 64 bits or 64 different wires. And this is why when you actually look inside these things, you see a ton of stuff. Now I should have brought that over. The PLC probably runs what we call a microcontroller. A microcontroller is a chip that has the memories in it, the ROMs in it, everything's in it to make it a computer, and then everything that comes out of it is nothing but I/O, which is probably what the microprocessor, what they do. Everybody okay so far? What does the address bus do? Good, it selects. We say it selects the device for communication. The control bus controls the communication between the selected device and the processor, and then the data bus is where the data transfer actually takes place. So they left off the control bus. So the bigger the data bus, the more bits we can transfer. The bigger the address bus, the more things we can select. The bigger the control bus, the more control we have over it. So on all microprocessors, these 2 guys right here, basically just size. The control bus is where things change between processors and processors. How much control do you have over the communication? Static RAM and dynamic RAM. Dynamic RAM. Now this is really fast, but static RAM is really, really fast. Dynamic RAM is really slow compared to static RAM. But dynamic RAM is extremely good. It's a lot cheaper than this stuff. Originally when we came out, they was using static RAM. The first processors that we started playing around with using static RAM. But they went to dynamic RAM because of cost. But they've done some neat stuff. Dynamic RAM basically works like little tiny rechargeable batteries. So what happens with batteries? They do what? They run down. So with dynamic RAM, we had to constantly do what they call a refresh, which is basically what you do with your cell phone. So very seldom do you let your cell phone run down, right? You understand? You turn itself off. You keep recharging it. Now, as long as I keep recharging it, then basically it should last for a real long time, right? Y'all understand that? So dynamic RAM works like that. So we call the recharging, they call it refresh, but it happens extremely fast. So all these memories we have, double data rate, DDR3, all these different types of memories, these are all dynamic RAM. But dynamic RAM's been around so long, the refresh is no big deal. They refresh it when it's not being used.
All right. So what's happening when I talk about outside that you get shadows?
Well, what you got to understand is these little things are acting like, I mean, they're so tiny. And all it takes to cause things to happen Is your cell phone ever locked up on you? One of the things you learn real fast is how to do a reset on it. Right? All it takes is one bit to change, and if it's an instruction, so what we have is we have a program that consists of instructions. An instruction consists of a binary code. Luckily, we don't have to deal with this. We call it a machine language that tells the processor what to do. And then we have additional information that tells it where things are at. And so all it takes is just one bit to change. And one bit could be, instead of telling it to go left, it now tells it to go right. So we have this happen all the time. What they're talking about shadow, I don't know. I just know you're not going to run into a computer that doesn't eventually lock up on. Because all it takes is one bit. And that's what you got to understand. This is why you got to know where to do it. Mine's done that before. The first time, guess what? I didn't know how to do it. I didn't know how to reset it. To get it back in its firmware, right? You'll understand. To get it back. So it's the RAM we have problems with. Firmware. So how would you do an iPhone to reset it? Hold the front button down, top button down for so long, and then it'll actually do a hardware reset. Or you can pull the battery out of it. A lot of times if you got one of these other phones, I think a lot of your Samsung phones still have batteries you can take out of it. Most of your iPhones, where's the battery at? It's embedded down inside that phone. And the only way you can take most iPhones to change the battery out, you have to do what? Take the phone apart. So you need to put that somewhere and have it done. I had an iPhone 3 and I went swimming with it. I just was going to take it apart. And I took it apart. I still got it apart. I could have probably got it back together. So what they did is they came out with a memory they put inside the processor called a cache memory, which is always static RAM. What the processor does is really, really neat. I'm not going to get into it. It constantly prefetches data. The algorithms, that they understand how things work. It's been around for years. They trimmed that down. So 99.9% of the time, the information that you need is already where? It's in there. So used to, we say, okay, the way processors used to work is I've got all these mailboxes outside. And the way processors used to work is they used to go out there and they'd go out to the mailbox, they'd get something out, and they'd come back in and they'd read it, and it says, well, you need the information from the next mailbox. So what do we do? Then go back outside, it'd go open up, get that letter, come back and read that information. It says, now you need the information from the next mailbox. So what they did is they realized that almost 100% of the programs out there are just nothing but doing what? They're just looping. That's all they're doing, looping. You're in there playing a game, that's all it's doing, it's just looping. So they said, why don't we just go ahead and put DRAM out there, all the mailboxes are DRAM, and I'm going to put this static RAM inside the processor we call it a cache. And what would happen, you say I want to load a program, it would go out to the first mailbox, instead of grabbing just that one mailbox, it would grab 10. And then it would come back into the cache, right? You understand? And you say go here, then it'd go out there and grab 10 more. Well, by the time it went through the program one loop one time, then where was the program at? It was in the cache, yeah, and now it screens. So that's the way processors run now. They run a cache, which is inside, it's RAM inside the processor. And they run different levels, so level 1, level 2, and some processors run 3 levels of cache. And they're all static memory. So you got the lower one is pulling in, then it's transferring it here, and so these guys will flat screen. It's just that when you change the sequence or something like that, it'll slow down just for a heartbeat while it's loading. DRAM, SRAM, mask ROM, programmable ROM. We already talked about these. Firmware, software. Everybody okay there? So firmware, you couldn't change firmware. Used to, the definition was firmware. You couldn't change firmware unless you changed hardware. Now that's not true. It's just that you can't change it. Odds are you don't screw around with thermal, right? Now most of them use these flash ROMs that can change, but very seldom do that. Address decoders, we looked at that. Peripheral. A peripheral is anything that communicates with a computer through a port. So technically, peripheral, we call it a peripheral vision, which is basically on the outside of our main vision, right? And that's what we mean, outside the computer. So anything that communicates with the computer through a port is called what? Peripheral. So they say we have a peripheral chip, which is probably true. So we usually have a unit inside the processor, inside the computer, that handles all your peripheral activity. You can't see it now, but used to it was two, but now they've got it down to one. Used to we called it a bridge. And we can see that. So this is called a motherboard. This came out of a desktop computer. And you can't see it. I pulled it out the other class. But the processor is under this big old fan assembly. We refer to this as a heat sink with a fan. And so the processor is under this thing, and then this chip right here, that's the guy right there. So this is the guy that controls all the ports. We call it a bridge. Technically, they call it a bridge. The book calls it a peripheral chip, which is controlling the peripheral.
That piece would be referred to as
The actual, what the book calls the peripheral chip. In computer, we call it the bridge. So this is the bridge between your high-speed data buses. Your peripherals, there's no way in the world your peripherals are going to run the speed of the address bus and the data bus, right? So it's like me sitting up here typing. How fast can I type? Well, I can't type in nanoseconds. So we got to have something that synchronizes my keyboard with me typing with the information flowing on the data bus. So we have that portal. That's one of the main reasons of the portal is to synchronize that. So I tap a key. It says, hey, there's a key out here. The microprocessor would jump off to the driver that says, okay, we need to run the keyboard. It would go out there and say, okay, who is that? Right, you understand it? Hey, it's me. And it says, okay, give me your information, but it's all synchronized. It's all synchronous communication. That data bus has got to be, everything's got to be synchronized. So usually when they say the speed, like they say 1.2 gigahertz, that is not necessarily how fast the processor is running. That is the synchronizing clock that's synchronizing everything. On these computers, the I/O bus is still running at 166 megahertz, which is still a lot faster than we never knew. So everything is synchronized with this clock. We call it synchronous communication. But this is the bridge. A lot of people want to call these ports, but these are not ports. These are the connection to the port. Where's the port at? Well, the port's on the computer, right? You understand? So this is where the peripheral we connect to the port. So we have USB ports, portal connectors. This is an old IEEE 1284, which we called it. This was a parallel port. This is the older type of video. We call this VGA. This right here does not have HDMI ports on it, portal connectors on it now. This is your audio. This is the way we used to connect our keyboard. This is called a DIN connector. Right here. And this is the one we'll run into on our some of our PLCs. We use this exact connector right here. This is not the actual port. This is the connection to the port, right? You understand? So the port is inside this guy right here. But if you look, you see all these hundreds of little connectors right here, these little paths. We call them foils or calls them traces. And some of them are squiggly. I'm not gonna tell you what those are. Those are inductors or filter now. I don't focus in. This normally we wouldn't let you handle this because most of the memory and the processor and everything on here is susceptible to static discharge or even difference in potential. So most of y'all are carrying a little bit of charge when you come up here. So don't touch it deliberately. Please don't don't pull out the memory here. Just kind of hand it on the side and I'll pass this around and let you look at it. This is the old hard drive interface. So this motherboard here's got some time on it. So yeah, this is where we used to connect our DVDs. We connect our DVDs and hard drives. We connect here. We call this a parallel ATA or advanced technology attachment. This is the port for the old floppy disk. And what we've done now is we've moved away from this and gone to a serial, what we call serial ATA, which is these connectors right here. So notice this is serial. This is parallel. We'll talk a little bit about that too. So I'm gonna pass this around and let you just look at it. I think I took the processor out last class and showed y'all that. All right. Just handle it by the sides. So since your cell phone is a lot smaller, and of course, if you want really high power processing power at your home, you wouldn't use a tablet, right? You understand that? And you wouldn't use this guy right here. You'd get you a nice desktop computer because they can put processors a lot faster because we can cool them down a lot better. You wouldn't use Wi-Fi. Unfortunately, a lot of the hardwired Ethernet has disappeared because everybody's using Wi-Fi. Address decoder, support chips. This is kind of misleading. So normally, we don't want the outside world connected directly to our insides of our processor, on the inside of our computer. So here's our computer right here. This is a port. But what we do is we do it through light, kind of like you do your remotes from your TV. So this is a perfect example. So at one time I said, when I get too lazy to go up and change the channel on my TV, that's, but now you can't even find a TV. Some TVs don't even give you the ability to change it at all without that remote, right? Well, what does that remote do? It sends out a light pulse. It sends out a pulse stream. Different pulse streams indicate you want to do different things. And then we have a receiver over here. So this is a light emitting diode LED. So this is a photo transistor, which basically picks up the light. So now, that's why if somebody gets in front of you, your channel changer don't work. You say, get out of the way, right? You don't understand that because you're breaking the light. These are built in. You don't actually see this. But what it does is it allows us to do stuff over here. If we connected this input device directly to our peripheral control circuit and something happened, like a lightning strike out there, it would blow up my PLC. So we isolated. They called it an optical isolator. So what would happen is that if something happened out here, it might screw this guy here up, but the rest of your PLC is still what? It's still working. So this is why most people, and if you don't have that, guys, you need to buy one. Those, for your computers. They work a little bit.
That's essentially like for a remote. You've got your switch there and one.
Yeah, so this is on your remote. This is on your TV. What they do on the PLC, if you pop this open, you see a little square thing. You've got six pins on it. It's usually yellow. Most of them's yellow that I've seen. So you see it as an integrated circuit. When actually it's an optical isolator. So if you did something out here and you mess things up, you might lose one of your input ports, But normally you don't use, if you use all your input ports, you got a big problem anyway. So normally, if you're good into, it's just like running cables, or a cable technically is a group of wires that's inside what we call a common jacket. Out at US Steel, if they were going to pull cables and they pulled exactly the number of wires they needed, then they didn't like that. They always wanted you to pull more wires. And why is that? Yeah, instead of come back and pull in a whole new cable, which is real hard, you can switch over. So technique is to get more input ports than you need and more output ports than you need. So if you blow up one of your input ports, then what could you do? You could switch over it, and you'd have to go back and make corrections, but that wouldn't take that long. And normally we use what we call tags, which is really cool. We'll talk about that a little bit. Where all you'd have to do is just go to one, and you change that one, and your computer would automatically do what? Change all of them. That references that input or that output. So that's why they use optical couplers. This is an AC module. So basically input, when we get an input bit, we can either have, DC, we can have AC or DC. So this is an AC input module. Your computer has no idea what AC is, because it's an electronic device. Electronic devices work off what we call direct current, which is current in one direction. Everybody understand that? Originally, the method for electrical control was AC. So when they came in and started adapting, instead of changing everything out in their system, they wanted a PLC that would be able to take the same AC that the electrical control circuit. So this is called a rectifier. A rectifier is a unit that converts AC to DC. So there's some parts missing out of this, because this would blow up that thing about it. So somewhere down the line, we've got what we call a resistor. How do I do it? Okay, there we go. Discrete is what they usually do. Discrete, this is digital. And what does digital mean? We're going to be right here. It's going to be true or false. So I would come out here, and this would be my switch. Close this, 120 volts. It's going to turn it into what? This is going to make sure it doesn't see what the input module needs. There's going to be a resistor in here. And then this goes into that guy. This is called an optical isolator. This would be an AC input module. So we can get AC input modules. We can get DC input modules, which is probably more popular. We're trying to get away from 120 volts as far as control goes. You still have to have high voltage for our power devices. But we're trying to get away from anything above 50 volts as our control circuit. And why they're trying to do that is that originally we had what we call the National Electrical Code. Anybody ever heard of the National Electrical Code? NEC. They never heard of NEC? NEC is a consortium of people that's got together. It's put out by the National Fire Protection Association, NAFTA. And what they wanted to do, these guys are all about fire. So they wanted to come out with a way that some rules that electricians would follow, so they could safely install electrical equipment. So they got out. We have this became known. It's the NAFTA 70 standard. This became known as the National Electrical Code, NEC. So y'all can research that. National Electrical Code. The problem is that number one, the NEC is not law; it's recommendations. So we have these electrical inspectors. So City of Birmingham's got their electrical inspector, Jefferson County's got their electrical inspectors, and before it becomes law in this local vicinity, then what they call it, the authority having jurisdiction have to accept it. And Birmingham is usually one. It takes a little while because they want to go through and check everything out on the new code. One thing that they realized was that the National Electrical Code is for the safe installation of equipment. Now, if you safely install equipment, then odds are it's going to protect you. But there was no set standard for how to protect you. So what they did is they came out with the NAFTA 70E. So most people just call it 70E. Who does that protect? You. And what they've established is that anything over 50 volts worth of push is considered to be a lethal voltage. So what happens as soon as you get up to 50 volts, there's a lot more to it. They call it calories. You have to calculate the energy level. Then you have to start wearing safety equipment. Above earplug safety glasses and non-flammable clothes. That's basically. So the more energy level you have, the more safety equipment you got to have. You got to start putting all these barriers and all this other kind of stuff, all these lines on your floor, indicating where you have to stay out from. So what they're doing is they're splitting up their power, where the high voltage is, away from control. So if they limit anything below 50 volts, that means you on a control circuit, you can get in there and work on the control circuit with just having basic safety, earplug, ear protection, eye protection, right? You understand that. So just about all your controls are going down to 24 volts, either AC or DC. We have 120 volt in here because we've had our trainers for quite a while. But I would like to be able to take a system that's designed around 120 volts and run it with a PLC. So we can buy PLCs that's got 120 volts. We can buy AC, 30 volts AC, DC. A DC standard for DC is 24 volts. And that's what, when I looked at my PLC, that's what this means right here. So when I looked at the PLC, the three things they specify is what do you need to power up the PLC on? Where's that over here? Oh, right here. So this says DC, DC, DC. So that means we power it on DC. My inputs use DC. And then the last one would be your output. If I looked at the Allen Bradley, it says AC, DC, relay. So that's the three things, and we'll look at that in a minute. So this Allen Bradley that I've got connected up here. Everybody okay? Let's take a 5-minute break, Scotty. Y'all let me go. I'll let me go right past. Anybody that came in late, you need to come up to my desk so I can make sure you get in row. Wait a second, let me bring up. If you left it past 8 o'clock, probably I did. It's been 5 minutes. So this is a little different. What they do is it's usually right in here. Is they'll put a device called a resistor. Because what happens is that normally this circuit right here is built for all the applications. And so what this guy right here would be looking for, it would be looking for a certain voltage, maybe 24 volts DC. Well, what happens is over here we get 90% of that. So over here we might get 110 volts. Well, if I put this into this, it would blow it up. So that's what the Zener does. The Zener, we call them regulators, and they actually take a big voltage and drop it down to regular, smaller voltage. No, this is your remote right here. Of course, they don't have to do that because yours is battery. So basically, your remote, every time you press that button, you're sending out a beam of light. Now this light is infrared, so you can't see it unless you got some cameras pick it up. So when you press that it sends out a sequence of pulses that would vary depending on what button you press on here. And then that light flashes. Of course, you can't see it. And then over on your TV, you have your photodiode over here. So that's why you got that little red screen over there. And what it does is it picks up those sequence of pulses, and every sequence of pulse would be you pressing a different button on your phone. Right, on, off. Yeah, of course, our TVs are never off, right? You understand that? Very few things that we have now ever turn off. We put them in standby. So you flip them in standby, or you turn them on. In standby, they're still conducting current, because if they wasn't sitting there running a program, your remote would do what? Yeah. So how do you turn a TV off? Unplug it. And then now your remote don't work. Now your remote's still working. Well, what they've done in the PLC is so if we looked at the PLC, we'd see this little old thing right here. Normally they have you would see this, but see these little pins going. That's all we see. So we see it as an integrated circuit, but that's your optical isolator, and it's built inside. So what happens here is if I come over here and do something I'm not supposed to, let's say I put 240 volts AC on that thing. Well, what's going to happen is it's going to blow that thing up. But what I've done, if I connected this into my PLC, what would that 240 volts done? It would have burned up my PLC. And now I'm screwed, right? You understand? But if it just wipes out that little optical isolator, then what can I do now? If I kept a spare input port, I can just do what? Just move a wire. Just take a wire that was plugged in over here and do what? Move it over to another wire. And then, but now you have to change your program. But the way the PLCs are worked is you go in there and you change it once, it'll automatically do what? It'll change everything. We'll see that. We can change these things all the time.
So this is essentially kind of like the ladder logic you showed us. So we have that one input port there where it says high.
Yeah, so I would come over here. So if I did ladder logic, this would look like this. I'd come over here and I do this. And then I'm going to come up here and this will be my input right now. And that would be my switch. And then I'd come over here and then.
Where does the rectifier fit into your ladder logic?
Well, you'll never see it. It's not there. Okay. All I see, I just come over here and I see this. I see a little screw called N1. Right. That's all I see. Because it's kind of different because we have input circuits and we have output circuits. We'll show you all that in a minute.
So I don't see any output on this particular, this is simply the input.
Yeah, so what we're going to do is we're going to program in ladder logic, but the inputs are not connected to L1. They're not connected to the load. They're connected to an input module. And then the processor reads that input module, and then it decides what it wants to do with the outputs. So literally it goes, the PLCs go like this. So I'll have an input button. Then I go into an input port. And then that would be right there. That's the load. So the load is the input port.
And in this case, is the remote. Or what is
no, that would be all this stuff right here. Okay. That little block I've got. And then of course we got to power it up. So this would be N. And then I would come over here and I don't have much room to draw on there. So my input circuit on a PLC. Now if I drew this as a motor control circuit, I would come over here and I would do this. A PLC, we got two circuits. We got one that's going to connect to an input port. And then the input port's got a common. And then we got another circuit over here, which is going to be the output port. And the PLC, this is going to be the output right here. And then my true load is going to be out here. That makes sense? So you got output circuits and input circuits. But when we program it, I don't need to know that. I program a ladder logic. And I'll assign an input address and I'll assign an output address. These are logical addresses. So when we assign addresses, we are not assigning physical addresses. Physical addresses are the address decoders that's inside the computer. Right? You understand? So in computers, the way I communicate with this computer right here, it uses something called a MAC address, which is Medium Access Control Access. It's a 48-bit binary number. How many of y'all know the MAC address of your computer? Well, if I want to communicate, what we usually use is what we call an IP address, which is an Internet Protocol address, which it's in decimal. That is a logical address. I can change the IP address for this computer. So when I go home, my network assigns it an IP address for my network. When I'm here at college, it gets an IP address for this network, right? You understand? If I'm down, okay, I take my cell phone into McDonald's, it gets an IP address for McDonald's network. So I can take if I'm using Wi-Fi, so IP addresses are logical, which means we can assign them and then it's unique for that network, right? You understand? So now all the routers and everything at McDonald's knows my computer's out there. If I come to my house, I get another IP. The MAC address never changes. It's a physical address. So that MAC address is a 48-bit binary number that's built into it, which is pretty neat. So the MAC address. So that's something we'll have to know later on when we do advanced PLCs. When I connect this PLC to my network, we have to know the MAC. And we'll talk about how IP addresses are assigned. But IP addresses are logical. So a logical address is software. And it can be all kinds of things, right? Understand that? Which is pretty. So all these addresses that you're assigning are logical addresses, which is pretty neat. So I can change, so that means I got this contact up here. I can say I'm going to use input 3. Okay, well, no, I need to use that down here. So I'm going to make that 4. You just assign these things by addresses, which is pretty neat. And there's a little more to this, but basically we have DC inputs, we have DC outputs, DC inputs. So this PLC right here, so this is Allen Bradley's PLC. So this says it's got what? It says it's got AC power. Oops. Let me get through. Yeah, AC power. Oh, I don't have it up here, so you can see. So here's where we connect the power up to this thing. And then it says it's got DC inputs. And it's got some analog inputs, which are right here. And then it says it's got, you read that? Relay out. So we can get different variations of those 3 on our PLCs or our modules. That makes sense? And we'll talk about relay out, which the book don't cover. So if I've got DC input, then we don't need that rectifier. But you'll understand that. So the rectifier wouldn't be on the DC input because that's what it expects to get. The rectifier would be on AC inputs. And then we have different types of, on our outputs. The outputs we can have, let me find it again. I'm upside down. We can have relay outputs. This PLC right here has DC outputs. What I like about Siemens is they put everything right here in this little block right there. DC, DC, DC. I mean, the one over here, this is DC in. I'm sorry, this is DC power, DC in, DC out. On the Allen Bradley PLCs, you got to do what? Yeah, you got to look for it. They put it around the outside. This is the 1100. This is the 1200 by Siemens. But what I want to show you is that these 2 PLCs are made by 2 completely different companies, but everything I've showed y'all so far is basically what? The same. Zener semiconductor device that maintains a steady voltage when low transistor becomes saturated. Okay, they say 5 volts. Of course, what you have to understand, guys, this is all transparent from you. What you're going to do is you're out here. Y'all understand that? All you got to do is make sure you hook up the right power to this thing, and that would be the right specifications. So if your input module is designed around, 10 to 30 volts AC, and you put 120 volts in the thing, what's going to happen? Well, it's going to bop it, right? But it's not going to bop the PLC. It's going to get that module or that input. If you got a DC input and you put AC on it, then you got big problems, right? You understand that? So that's all you got to know. All you're looking at right now is you're looking at it where? This is where you're at right here. This is what we're dealing with. All we got to do is establish a common, and then what we call a hot lead, which we'll look at. And the same thing's true on outputs. Except output, we add another. So on the inputs, they're either going to be DC or AC. Period. On the outputs, we got 3 options. We got AC, DC, or relay. And what's nice about relay is that you can wire it AC or you can wire it DC. Either way. This divides the sections up. I don't know what they mean by an octal latch. This is an AC output right here. Oops. It uses a semiconductor called a triac. And what it does is allow a triac, we can trigger it with DC. And some people call these solid state switches. So if you've got motion detectors at your house that come on at night, it uses a triac. That's all it is. It's just an AC switch. It's a solid state AC switch. It's not a relay. So we have triac outputs. So an AC output is going to use a triac. A DC output is going to use a transistor, and we'll talk about that later. You say they're going to use a PNP or an NPN transistor. And then a relay output, your module is going to control a coil, and then we're going to have a contact that you don't see. That's going to, what's nice about a relay is you can hook up what to it? AC or DC. So we established a common. So if we look at the Allen Bradley PLC, if this, y'all can see this, guys. It has a relay output. And down here on my outputs, is it going to focus in on it? Ooh, no, it's not. Come on, guys. Come on, guys. So here's all my outputs, and you can't hardly see it. There's a jumper between that. But what we have is we have it's got DC AC. So you put in on this, there it goes. On this screw, you would put in DC or AC, and then this right here would be your output. This is output 0. This is DC AC. This is output 1. This is DC AC. This is output 2. So what's the beauty of this is you can have this one right here switching DC. You could have this one switching AC. You could have this one switching DC, right? You understand? You could have this, and then you would see what voltage. This might be switching 26 volts AC. This guy right here might be switching 120 volts AC. So this is, Allen Bradley does that. This Siemens, you get what, the Siemens right here, you get what you get what you buy. It's DC output. All we have to do is just establish a common right here. So this says plus DC. So I put my whatever DC power supply I was running this off. I could run it maybe on different levels, but that would be part of the specification. Are we okay? Are we okay? Analog digital converters, we okay there? We talked a little bit about that. So we live in an analog world, right? You understand? These guys don't work off analog, they work off digital. So if I'm going to communicate analog, like the speed of a motor, the speed of the motor is not digital. Speed of the motor would be analog, right? Temperature is analog, right? What does analog mean? Constantly varying. It has the ability to vary. But what we can do is we can bring it into a special chip called an analog to digital converter, which takes that information and converts it over to binary for us, ones and zeros. And then once it's in binary, what can my processor do? I mean, it can analyze it, right? Then if I want to control the speed of a motor, if I wanted to control the speed of the motor, that's also analog, right? You understand that? So we have what we call digital analog converters. Those have a name. Those have an acronym, DAC. ADCs, we just call them ADCs. Okay? This one has 2 analog input ports. This one has 2 analog input ports, but this little module we stuck right there gives us an analog output. So what I would do is, in my program, I would store a binary number into that port, and it would automatically generate a voltage that was equivalent to that binary number. Timing count. So these are some of the things we got. We got timing, and these are instructions. So an instruction is something we put in a program that tells the processor what we want to do. We have input-output instruction. We got timing instructions, counting instructions, data manipulating instructions, reporting, arithmetic, logic, and communication. So all the instructions that we're going to look at, we're going to do down to right here. We got so much to learn, right? Just to get to the point where we can do inputs and outputs. Right? The advanced PLC will deal if you take that class. How many times have I taught this class? Huh? I've never taught this class. Huh? No. But I do teach advanced PLC. That's this chapter here, guys. Y'all got any questions? Anything you want to drop back and go back over? This is chapter 1. And then we're going to look a bit at, we touched on chapter 3. We're going to look at chapter 3, then we'll come back to chapter 2, and we'll start getting more specific with, so there's a lot of things in chapter 2 that we don't understand unless we get a good feeling of chapter 3. So the next chapter we'll look at is chapter 3.
You said our live going to be this week.
Probably not. The first lab that y'all do, I think it's lab 1, is numbering systems. And that's a homework lab. Y'all look at that, the lab book. If you don't have your lab book, guys, I'll look at it. What's the first lab in the lab book?
It's just asking questions, describe the differences between Allen Bradley, Slick 500, yeah, that's one. Like an overview.
And then what's lab 2? I don't have a copy of lab book either.
How do you address the output ports available?
Okay, in 1 it only has that one activity, it's just like an overview, and then once you go to activity 2, again, it's sort of asking review questions to see. And that you only have 1 page each for chapter 1 and chapter 2.
Yeah, I think the first 2 labs would be homework labs anyway, right?
They can be. Let's do it hard and have some. I need exactly the same. I think actually